So in the last video, I mentioned that Chapter 2 was going to cover these three topics. The first is drawing inferences about single individuals from a normal distribution where mu is known and the variance is known. And then secondly, more realistically, think about drawing inferences about the population mean mu, where obviously mu is going to be unknown and the variance is going to be known. So up here, both the mean and the variance were known, and we're dealing with single individuals. Down here, we're not dealing with single individuals, but rather the population mean, and mu is going to be unknown. And then the most realistic situation is when we're interested in drawing inferences about the population mean mu. Obviously, mu is going to be unknown. But now, more realistically, the variance is going to be unknown. And it's going to be estimated by the sample variance. But this video is going to focus on this topic, thinking about the characteristics of single individuals drawn from a normal distribution in which both the mean and the variance are known. One of the tools that's going to help us a lot with that is the standard normal distribution. So let's just start with just a regular run-of-the-mill normal distribution. So we got y here, we got f at y here, and then we've got a normal distribution, and we might say, okay, it's got a mean of 100 and a standard deviation of 15. So one standard deviation in this direction would be 115, and one standard deviation would be in this direction would be 85. And what we're going to do in order to solve problems is we're going to convert from our assumed normal distribution to what's known as the standard normal. So here we've got y, and here we've got f at y. There's our normal distribution. But now what we're going to say is the mean is equal to 0, and the standard deviation is 1. So we've got a 1 here and a -1 over here. Now, this distribution, this really special distribution, the standard normal distribution, is so common that oftentimes, instead of using y and f of y, what we'll use is z. And the formula for z, it's going to become really important when we try to solve problems, is that z is going to be calculated by taking y minus mu, and dividing by sigma. So, for example, if we had a normal distribution with a mean equal to 100 and sigma equal to 15, and we had a y value that was equal to, let's say, 110, then this corresponding z score would be equal to 0.667. So whereas on our run-of-the-mill normal distribution, there would be our value here of 110, the 0.667, when we've made that transformation to a standard normal, would be shown there. Okay, so now let's try to solve three different types of problems. And the first problem is we're trying to determine the proportion of individuals, or the percentage of individuals, or the probability of an individual selected at random having a value greater than some specified value. So what we're going to use as our example is IQ, because I said in this video we're going to be talking about those unrealistic situations in which both the variance and the mean are known. And that's one of the things about IQ, is that we can assume that the mean is equal to 100 and the standard deviation is equal to 15. So in our first problem, what we want to know is if we have an individual with an IQ of 130, what proportion of the population is going to have an IQ greater or lesser than that particular value? And so the way we solve problems like this is to calculate our Z statistic so we can use what's known as a Z table. So we calculate Z is equal to 130 minus mu, which is 100, divided by 15, which is equal to 2. And once we've got our Z score, then we can use our Z table. So let's go look at our Z table. So this is our Z table. It's present in the appendix in your notes. And what you have in the body of the table, all these numbers here are proportions, and they're the proportions that lie within this area. So we said that we had a Z value of 2. So if we got a Z value of 2, what proportion of individuals would lie in this area? So the way the Z table works is that the first digit's shown here and the second digit's shown here. So we want a 2. There's a 2.0 there. There's 2.0. This would be 2.03 would be there. So for a 2.0, you can see for a 2.0 that 0.97725, that would be the proportion here, 0.97725 would be here, and the remainder would be out there. So now that we know that, we can say that if you had an individual with an IQ of 130, then 97% or close to 98% would have an IQ of less than 130. So for our second problem, what we want to do is determine the proportion of individuals that have an IQ going from 90 to 120. Or another way to look at this is if you were to select an individual at random from a population which has a mean of 100 and standard deviation of 15, what's the probability of an individual having an IQ in this range? So as always, we're going to begin by calculating our Z values. So we'll begin for the Z of 90. It's going to be equal to 90 minus 100 divided by 15, and that's going to give minus 0.67. And for the 120, we get 120 minus 100 divided by 15, which is equal to 1.33. And so with those two numbers in hand, let's go to our Z table. So here we are at our Z table, and the two Z values we've got are minus 0.67 and a positive 1.33. Now, the whole idea about Z tables is that we don't have any negative numbers. So instead of considering minus 0.67, what we're really going to consider is 0.67. And then we're eventually going to see how we can use that positive 0.67 to answer our problem. So 0.67, let's find that. So there's 0.6, there's 0.6, and there's the 0.7. So if we take this number here, we get 0.74857. So what does that represent? That represents the proportion here, 0.74857 is the proportion of individuals having a Z value of less than a positive 0.67. And then we can do the same thing for our 1.33. Here is our 1.3, and there's our additional 0.3 right there. And so the 1.33 translates into a value of 0.90824, which says that 0.90824 is the proportion lying in this area with a Z score less than 1.33. So, with those numbers in hand, we can do some calculations. So, what we just saw was that if a z-score was positive 0.67, then 74.857 would lie in here. And then obviously if 74.857 lay within here, then 25% or 25.143% would lie out here. But again, what we're interested in is not a positive 0.67, but a negative 0.67. But what's going to save us is that the Z distribution is symmetrical. So if we know that 75% is greater, has a greater value than 0.67, then what we can say from that is that 25% are going to have a value that's less than minus 0.67. So if we think about our standard normal curve, and we've got a Z value of minus 0.67, we know that 25.143% of the individuals will have a value less than that particular Z-score. The other Z-score we got was 1.33, and that told us from our Z table that 90.824% of the individuals would have a Z-score less than 1.33. But what are we really interested in? We're interested in knowing the individuals, proportion of individuals that have a value between 90 and 120. In other words, the proportions that have a value of between minus 0.67 and 1.33. Well, here is the proportion that's less than minus 0.67. So this value here is proportion less than minus 0.67, which is 25.143 is in this area here. So if we know that 90% is in this whole area and 25% is in this area here, then it's easy to determine the percentage in individuals that are lying in this area through a simple process of subtraction. So we got 90.824% are lying in this whole area here, and 25% are lying in this area here. So if we take the difference between those two, we get the percentage that lie in that intermediate range, and the value that's associated with that is going to be the difference between those two, which we can see is going to be equal to 65.5681 will be the percentage of the population that have an IQ that lies within this range. So the last problem is to ask ourselves what sort of an IQ would be needed to have an IQ that was greater than 99% of the population. So, as always, we use our formula. Z is equal to y minus mu over sigma. We know mu is equal to 100. Sigma is equal to 15. Y is our target. That's what we're trying to determine. Z. How are we going to get Z? Well, we know that we're interested in a Z value. What we need is a Z value associated with 99%. So off we go to our Z table. So in order to solve our problem, what we need to do is get the value of Z, which is associated with a probability of 99%. So we look at our Z table, and there is the value there, 0.99010, which is the closest to 99% that I can get. And so what's the Z value that's associated that would give us 99% in this value of the table? It is 2.33. So with that in hand, we can go back to the whiteboard. So here we are back at the whiteboard, and we determined that the Z value associated with 99% of the population was 2.33, and that's going to be equal to Y minus 100 divided by sigma, which is equal to 15. So we can solve for Y. We can solve for Y and say that Y is equal to 134.95. So in other words, an individual would have to have an IQ of about 135 to have an IQ that's greater than 99% of the population. So we'll stop there, and in our next videos, we'll see how we can draw inferences not about single individuals, but rather about the means of populations.